Okay, there you go. So, again, thank you all for coming today. Yeah, let's start from. So we last week we discussed that we were going to cover mainly 3.3, 3.4. We focus on Chinese remainder theorem and modular universe and also Lagrange interpolation. So that's the few topics that specifically we want to go a little bit deeper into. But just for to include everyone, anything that it's like anything before Chinese remainder theorem. For congruence, like 3.3.1 and 3.3.2, anyone have any questions, things they want to discuss? I'll take the silence as a no. So, okay, then let's go to 3.3.3 Chinese remainder theorem. Again, yeah, so before we go into this, yeah, any parts of this that you do not understand for 3.3.3 that you want to talk to us about, you want to ask about here? Wow, everyone understood this. Did any one of you try to implement, for those that more technical, did anyone if you try to implement the Chinese remainder theorem in code? No? Okay. It will be fun though. I would love to see someone do that. That will be quite an interesting thing to see, and will help you probably learn a lot. It's fine, you know. So, okay. So 3.3, I assume there's no one has issue with 3.3 then. But yeah, just for the sake of it, um, let's try to go through one of the examples over here. So yeah, example 10. Um, so looking at it, so okay, so for congruences, essentially, right, when we talk about using the Chinese Riemann theorem to solve a system of congruence, what we essentially want to do is to find some value for x that satisfies all this, right? Given some value of x, it's congruent to 4 mod 7, 1 mod 3, 3 mod 5, 0 mod 11, right? So in order to do that, they actually give us the full steps here, but essentially, let me see if I can pull up some notes here. Yeah, it's fine. So essentially, we want to find a x value that satisfies all this. So to do that, we can start by doing, if you have pen and paper, feel free to do it on your end. I am going to do it on pen and paper that I cannot really show here. Let's see. I'll try to get a. Let me see if I can annotate this. Annotate. Okay, so is that okay? Great. Can I just nope, I cannot do that. I will need to clear all the drawings. So, there you go. Nice. So first, let's focus on this two. To actually do for this four, let's focus on these two. So let's find a value that is equal to 4 mod 7 or 1 mod 3. One very simple way of doing this is essentially just I mean it's essentially you have to go through each of them, right? So 4 mod 7, what is 4 mod 7? Well, 4 is 4 mod 7, uh, 11 is 4 mod 7, and so on and so forth. Right? What is 4 mod 7 and also 1 mod 3? So actually, interestingly enough, 4 is 4 mod 7 and also 1 mod 3 in this case. I believe, yeah, 4 mod 3 is 1 mod 3, right? So that's our first, so that satisfied these two, right? And so now we want to find out this, okay? So let's do just, okay. So we'll also usually combine this because 4 mod 7 and 1 mod 3 essentially it's also equivalent to 4 mods 21. Okay. Okay, great. Yes. Okay. So now let's find something that is also let me just sorry, let me just this is a bit confusing. Let me just remove this. So we found 4 here. So since we found 4, we want to find something that satisfies this and also x um, equals to 3, right? So to do that, x congruent to 3 mod 5. To do that, let's find something that satisfies the above and then this. So to do that, essentially, you have to find usually an increment of 21 because you want it to satisfy the above, right? So something that satisfies both of this will needs to be in mod 21 essentially. Because if you just take one of it, like let's say we just take mod 7, it might have some that does not satisfy the second congruent, right? Similar, yeah, the systems of congruence essentially. So 4 plus 21, so 4 mod 5 is obviously 4. Plus 21 will be 25 in this case. 25 mod 5 is 0. Plus 21 would be 46. 46 mod 5, it's 1. So this is 4, 0, 1. And then we plus 21, which is 67 in this case. And this is 2 actually. And we continue, plus 21, so 88. Yes, 88. Mod 5. 88 mod 5 will be 3. Okay, great. So it's 88. Okay. So here with this two, we know it's 88, right? 88 x is 88, right? So here since 8 is 88, so we can also basically add this up. So 88 mod 21 times 5, it's I think it's this should be. Let me just, yeah, I think this is correct. 105 should be. Yeah, yeah. So 88 mod 105, yeah. So now 88 mod 105, we have this. Now so let's do this. Okay, oop, oop, oop. Oh, this is quite useful. I should use this more often. Anyways, so now we have this. We can now try to calculate this, right? The last one, 0 mod 11. So to calculate this, again, this is kind of the, so to say, more brute force method. If you implement the algorithm, obviously it becomes a lot easier to calculate via computer, right? So yeah, so from here, let's look for something that satisfies all of the above and also will be congruent to 0 mod 11, right? So 88, let's remember it's plus 105. My handwriting's getting worse here. So 88 mod 11, actually that's 0. So I don't even need to do any more calculation. 88 mod 11 is 0. So you divide is 8, right? So it's 0. So we know x from this calculation, right? From this calculation, we know x is 88. Or more accurately represented, x is 88 mod 7 times 3 times 5 times 11, which is the answer is here, so it's 1155, right? I'm gonna copy this. Yeah, so that's essentially how we calculate the simultaneous congruences, right? Via the Chinese remainder theorem. Okay, let's see if I'm right. Oh, I can't scroll with this, so I'm just gonna clear everything. 1, 2, 3, boom. Okay, great. What's this? Okay, so is it 88? Yep, so it's 88 mod, in this case, 88 mod 1155, right? And you can see here that it tells you that the set of all solutions is this, because remember in modular arithmetic, well, there is a lot of possible solutions other than 88. right? And you get all this set. If you are a little bit confused how you get all this set, it's essentially via 88 minus or plus, right? It goes up or down, right? In this case. Yeah, so that's essentially it. And if you have Sage, you can do this. So I'm just gonna copy this. If you have Sage, you can try to do this on your laptop. Okay. Let me just do this. Whew. Okay. I need to clear this. Can I clear this? Nope, I cannot. Turn on Kitty again. Sage. Welcome, latecomers, by the way. So yeah, see, so this is essentially doing the same thing that we did, but a lot faster. But yeah, so follow along if you can, great. Okay, so that's essentially just a brief go through of this. You can also see like they do use something like this. This is essentially the extended Euclidean algorithm that we mentioned last week in very little detail. We just went go through it by passing. It's the GCD. Um, you might know other ways of calculating this by hand. It's slightly different, but yeah, it does this, right? Anyways, so that's that. That's a very quick one. Go through of the Chinese remainder theorem. Any questions? Oh, let's see. Oh yeah. Oh, that's great. Sage cell works. Yeah, yeah, yeah. It should work. Let me see as well. Yeah. I personally don't like the UI there. I think there's another one called Co something that someone mentioned in the group. Um, but yeah, if you can use the link that B just mentioned in the chat, yeah, use it. It's fine. It does the calculation. Should do the calculation fine. Yeah. Cool Clark. Yes, thank you very much. Get Gerald. Yeah. So yeah, you can do this, right? This is obviously faster than what I've tried to do here. And most of the time when you work with ZK, there is library out there, but if you need to implement it by hand, it does help a little bit to know how to calculate it. Um, you know. Anyways, so I'll assume there's no questions so far. Okay. If that's the case, let's go.
Um,
B, go
Sorry.
ahead. Yeah, no problem.
I just in the outside, so I would,
I know.
yeah. I'm not sure on the process of the Chinese remainder algorithm that why do we have to do the extend Euclidean algorithm here? I mean, like I'm trying to put this one through.
I see, I see. Um, I think in this case, so what I've manually done is essentially I'm looking through all the possibilities, right? But what is essentially done here, it's trying to find, so in each step, um it's essentially trying to find the x value for let's say n1 is trying to find um so negative 47 9 times 7 is this one, right? So it's getting
Mhm,
the GCD of 7, and in this case 165. 165, it's obtained via this division, right? This 117 time this is the essentially this is the product of all this modular. And by dividing by 7, you get essentially this value. This value is not exactly the result of um what we've done just now, but they are trying to essentially do these steps here. So this is the more algorithmic way of doing it. They are essentially trying to do this and then calculate via Euclidean algorithm to get um, the value, the values required to find the next step of what we've gone through just now. So remember just now we first find some x value that satisfies these two, and then we try to find some x value that satisfies all three and then go to four, right?
mhm,
That's more of a calculation on hand. So this follows this algorithm here. It does essentially similar things. But yeah, it's more computer friendly, I would say this, because if you want to implement what we've done just now with a program, it's essentially like quite a lot of loops, right? You need to find this, and then you need to generate all the possible modular that satisfy both, and then you have to generate again. You have to generate again. It grows with the amount of simultaneous congruence. In this case, it's I think faster. At least it's not n more than n square, I believe. Is it n square? Yeah, might be more, maybe n square, but yeah, it's definitely more efficient to do this on a computer than this. Yeah.
Okay, I guess. Yeah, I
Yeah, I
mean,
mean,
is it actually some algorithm that we would do it on the computer rather than the just calculate by hand because the value is so vast.
yes. It's so what we are working with here right now, it's very small congruence, right? Um, so these are pretty easy to calculate by hand. If you try to do larger values or if you add more, like if you do something that's a mod some prime number, some very large prime number, it's a lot harder to do by hand. Because you've seen just now, I mean, I'm already struggling a little bit, although it's like just like hundred something, right? Thousand something,
Mm-hmm.
right? So you can imagine if it goes like to a huge amount, this will be a lot better to calculate. I believe, yeah. But if you look at what they are trying to do here, they get this value here. It is part of the formula that's introduced here. But yeah, it achieves the same thing. It's just I think this is a little bit more formal. Harder to understand definitely. But it does the same thing. It's trying to find some value that satisfies all of this.
Satisfy of That's only one value that satisfy all the congruence, right?
To be fair,
Like
there's a set. So the set is this.
I see.
We are finding the smallest value that's non-negative, which is nicer to represent. But technically, anything that mod 1155, that's 88 mod 1155, right? Would
Mhm.
be there's a lot, right? So you 88 plus this will still be mod, like when you mod it by 88, it's still going to be 88. So if you mod it by 1155, it's going to be 88. So what I mean is, let me just try to see, let's see if I can write this. So it's in this set because 88 mod 1155, it's I mean it's 88, right? But technically 1247, which is equals to 1155 plus 88 mod 1155 is still 88, right? So yeah, the answer you get is 88 mod this, but it's actually a set, right? The solutions for this is a set. But yeah,
Mm.
you're right to think that 88 is the answer. It's just that to be a little bit more specific or a little bit more, I guess, accurate, it's a set of numbers that is this. Yeah,
Mm.
yeah. The negative numbers does the same thing. It's just minus, right?
So if I understand it right, so 88 is the we can say 88 can be used for the all congruence in the problem at the first, right? The four x's above.
You mean for you
Yeah,
can say
yeah.
88 is the answer for this? Yes, yes. So
Okay,
88 mod 1155, it will be the answer to this. Yes.
okay. I think that kind of makes me a little bit right now.
Great, great, great. Yeah. Thanks for the question. Always appreciate it. So any more questions? Don't be shy. You're also free to answer questions post, by the way. Okay, then we shall move on. Okay, great. Um, so there's also remainder class representation. So this is yeah, this is essentially we are trying to do remainder class for the remainder, you get the following. So this is essentially let's look at an example, right? Choosing the module n equals 6, we have 6 remainder classes. And this remainder classes essentially is what um how do I put this? Okay, so when you say given modular 6, right? 0 modular 6 can be the answer to 0 modulo 6, or like what modulo 6 is 0, can be a set of values, right? And same goes 1, 2, 3, and 4, and 5. So this is essentially the remainder classes, so to say. Yeah, that's essentially what it's talking about. I'm gonna quick skip this. But if you have any questions on this, yeah, tell me. So the next important part. Okay, so before I continue to the modular inverses, also to answer some questions from last week as well. Um, there was question on, hey, we are learning on like we are talking about, well, we are learning modular arithmetic and polynomial arithmetic, learning about all this remainder theorem, modular inverse, like why are we learning them? So actually, so for Chinese remainder theorem, it's actually used in cryptography and particular implementation of FFT. So what part in cryptography one might ask? So one example is Shamir secret sharing, which is it's not, I guess it's not ZK, but it's MPC, where you essentially shard your secrets to multiple parties, and then only when you have enough shares that you can recover the secret. So these are the building blocks of ZK and other cryptography. It's like the primitives to them. That's why we learn about this, right? It's to help us understand it, and hopefully, maybe in a future workshop, we can implement it. You know, that's the goal. To build something useful of this. Okay. Anyways, modular inverses. Again, any questions before we maybe go to one of the examples? Any questions you've had after going through this section last week? Anyone? Mm, great, great. Oh, you guys are really good at understanding this. This took me a while. That's great. Then we can, so let's just go to look at the example here. Module inverses, essentially what inverses are, the multiplicative one at least. So let me just find something. Yeah, so inverses is something like this. Yeah, so inverses, generally speaking, multiplicative inverse, when we talk about it, it's this. Yeah, a times a to the next one, a inverse, right? Is equals to 1. So this is an inverse. So let's go through an example, shall we? I'll go through one, and hopefully one of you will go through another one. Well, we'll pick later. I might be, yeah, just prepare yourself. Anyways, so let's try to go through the simple ones here, I guess. Where is the, I want to find the example that they provided. Actually, no, it's not here. Hmm. Yeah, but yeah, there's also a way of doing it where they calculate. We can actually calculate residuals R in modular arithmetic, and this basically gives you the inverse. Yeah, so let's go through this example, shall we? Take so oh sorry, let me just first. Where is it? Okay, so here, they're trying to find. There is a chance where you do not get there's no inverse, right? Um, for example, for the value 2 in modular 6 arithmetic, there is no inverse for 2 because 2 and 6 are not coprimes. So sorry, 2 and 6 have a GCD of 1, so they are not coprimes, yes. Does not have a GCD of 1. Sorry, I said the wrong thing. Yeah, they are no coprimes. 2 and 6 has a GCD of 2, I believe. Yes, 2. So that's why they are not co-prime. That's how you know they're not co-prime. And in that case, there's not really a inverse of 2, multiplicative inverse of 2. But for 5, so for mod 5 arithmetic, in this case, let's say here they actually, so yeah, this here. So here they actually talk about, let's see, where do I, okay. So 5, so for 5, let's find the inverse of, let's say, 4. So to find the inverse of 4 in 5, one way is to use this RRP -2, right? And you can find, so in this P is 5, and R, R is, I believe, the value itself. So it's 4 to the, let me just get a calculator, not calculator, sorry, annotation. Sorry. 4 to the 5 minus 2. Remember to mod 5. So the inverse of 4 using this method should be 4 to the power of 3 mod 5, which should be equals to it's the 4 to the power of 3. Let's just cheat a little bit. 64. 64 mod 5, which should be equals to a 4, actually. What? Yeah, 4 mod 5. So it's its own inverse. Yeah. So that's how you, is that correct? Wait, let me think. Is that correct? It's congruent to -1 mod 5. Yes. Yes, you are also right. But -1 mod 5 is technically 4 mod 5 too. Yeah, but if it's, I guess if it's just integer positive integers, it's 4 mod 5. So it's its own inverse in this case. I think it's right. From my understanding, it's right. Hopefully I don't understand this wrongly. But yeah, I think that's an example here. So this is 3. So in this case, 3, the inverse of 3 in modular 5 arithmetic is 2. Oh, where am I? Okay. Yeah, it's 2. Yeah. And if the inverse of 3 is 2, then the inverse of 2 is very likely 3. Yeah. So anyways, yeah, that's one way to get this is one way to get essentially, or calculate essentially how the multiplicative inverse of in some modular P arithmetic. Yeah. Thank you for the, yeah. Anyways, yeah, so you can also try to find some inverse of a polynomial here. But it will need to be in modular, some modular arithmetic. Yeah. So in this case, let's look through this. 3x plus 3 plus 0. Yes, following. Yeah. I think this is, anyway, modular. Oh yeah, this is just showing the difference between non-prime number modular arithmetic. Not really inverses. Okay, sorry. Okay, but yeah, let's look at this then. So consider the modulus this. Which of these values have multiplicatively inverse in modular 24th arithmetic? So in this case, we have to first know calculate if it's a co-prime. Here. So 7 is not a co-prime, I guess. Wait, I don't believe so. Let's do the GCD of this. No, they are a co-prime. Yeah, they are a co-prime. Sorry. Yeah. 1 technically is a co-prime. 0 is not a coprime. 805 is a coprime. And this, let me see. Wait. This, I believe, also is a coprime. Yeah. So I believe other than 0, all of this should have multiplicative inverse. I'm not gonna do the big numbers because I'm lazy. But yeah, let's try to compute the inverse of 7 and 1 in modular arithmetic 24, right? Because GCD is GCD of 10 to 4 and 7 is technically 1. 1 and 24 is 1, I guess. Yeah. So let's find, you know what, let's just find 7, right? I'm a little bit lazy today. Okay, so how do we find it? Again, RP minus 2. In this case, 724 minus 2 is 7 to the 22. I'm not going to calculate this by hand because it's insane. Sorry. That's also insane. Let's just mod this by 24. Can I just mod here? That doesn't make sense. Wait, 7, 24 minus 2 are 7 and 2. Yep. 1. That doesn't really make sense to me. Wait, is the calculation wrong? Just this calculation. Make it mod 24. No, it's 1. Apparently so. So the inverse of 7 in 24 modular 24 arithmetic is 1. Huh. Okay. Oh, yeah, wait. Great. Yeah, it just didn't seem right in my brain. But yeah, so yeah, using Fermat's-Slater theorem, yeah, that's how we calculate it. So yeah, you can do the rest. And that's it. For modular arithmetic. Sorry, modular inverses. Any questions? Yeah, 24 is not prime. The inverses are really weird. Yeah. Any questions before we move on to our final topic that we want to cover today?
So, hi,
Yep.
hi, Wenkang.
Hi.
So having an inverse means so multiplying 7 to 1 in modular arithmetic 24 is gonna become 1, right? Like the whole meaning of inverse.
Let me think. No, in this case, I don't believe so. So 7 and 1, it's not. So 7, if you take 7 mod 24 times 1 mod 24, it's going to be 7 in this case, right?
Yeah, that's
And
why I was a bit
yeah.
confused.
So it's really weird when you talk about when you talk about this in non prime number. So let's take
Non-prime number. Okay, yeah.
let's take if you talk about prime number modulus, I think it makes a little bit more sense. For example, just now we calculated
23.
4 mod 5, its inverse is 4 mod 5, right? 4 times 4 is 16, mod 5 is 1, right? It goes back to 1. And for example, 3 and 2, right? 3 is the inverse of 2, 2 is the inverse of 3 for modular 5 arithmetic. And 3 times 2 is 6, 6 mod 5 is 1, right? So
Mm-hmm.
in this case, it kind of doesn't make sense, I guess. Um, but I think if you do it in a prime number, this might be a little bit more sane. I'm not sure about that. But yeah, it will make a lot more sense in
Hello?
yeah, sorry, yeah, go for it.
No, so his question is like what's the definition of a modular inverse? So yeah, in mod 24, the inverse of 7 is 7 because 7 times 7 is 1. Because it's like what's the modular number equivalent to 1 over 7? That's like the definition of what an inverse is. So yeah, and then going back to your other point, when you're in prime world, so it's like if you mod a prime number, generally like all the numbers will have like a friend or like a pair. So like 2 and 3 are like inverses of each other in mod 5. But then like usually the prime minus 1, which is like mod 5 is 4, then that
Yep.
is always an inverse of itself. But then the other members will have like a friend. But in like mod 24, then there will be weird things. Some numbers don't have inverses, some do. But yeah, generally the definition of a modular inverse is
A times A to the inverse, it's going
A
to be
times
1.
B. B is A times
Inverse.
B, and if B is the inverse of A, if the result equals 1. In any case, you can A and B can be the same thing.
Yep,
Right.
there you go. That's it. Thank you, Wade, for
Thank
the
you. Thank you. Thank you
explanation.
explanation. Thank
Yeah.
you. Yeah.
I'm not very, very familiar with non-prime modular arithmetic. But yeah, thank you, Wade. Really helpful. Any more questions before we go ahead, or anything we want to talk about? Great. Let's proceed. Yeah. So 3.4 polynomial arithmetic. So yep, we talked about univariate polynomials last week. Division, prime factors. So the main point we want to talk about is Lagrange interpolation. So before we get in here, any questions on 3.4? Well, okay, great. So then let's go into Lagrange interpolation. So yeah, this is something that we'll constantly use in various ways. In this case, yeah, so this is something that later on, so in Graph 16, the Graph 16 protocol as well, we'll use this in a lot of, I believe, in almost all, if not all, ZK protocols. We do use this in different ways. We do use FFT in place of the original Lagrange. I mean, we're still doing interpolating, right? But we're using SFT to make it faster. But yeah, the idea is the same. This is a technique that we use to for the calculation in a lot of the protocols, and that's why this is essentially quite important here. So yeah, any questions on this? Anyone who tried to implement this, it will be quite fun implementing this, I think. But yeah, anyone? Questions? Okay, if not, let's go through an example. As usual, Asilvac, come on, should have tried. But yeah, let's go through an example for this. And then yeah, let's see if we get any questions and also on. So, what Lagrange is, simply is essentially it's a way of, so given some points on a, what's that called? Some points on the plane, on the graph. Yeah, some points on the Euclidean plane. I guess that's called what it's called. Yeah, Euclidean plane. Yeah, axis. Yeah. Given some points, given m point or m plus 1 points, you can calculate a m degree polynomial. So essentially, yeah, that's a very simple explanation of it. But essentially, you have some points, right? You have some points. Sorry. Every time I draw on the words, you have some points. Ta-da, ta-da, ta-da. There's some points, right? Let me just draw simply points. You have some points. Yeah. And essentially what Lagrange interpolation does is it draws the line, and this is usually a polynomial in this case, right? And if I have 4 points, you can at most get a, is it at most? I might be wrong, but we can get a degree 3 polynomial, right? And if I have more points, you can get something higher as well. But yeah, that's essentially what Lagrange interpolation is. And we're going to go through 2 examples here, just so that we see how it works for non-modular arithmetic math, and then we see how it works for modular arithmetic. So here, given some set S, right, 0, 4, -2, 1, 2, 3, we want to compute like a polynomial of degree 2 in this case. If you look, let me just cancel this for a while. If you look here, they gave like a algorithm that you can use. I'm going to use this because I don't really know really other very efficient way of calculating this. But yeah. So let me just take this. Okay, great. So it essentially calculates. So for these 3 points, it needs to do these 3 calculations for essentially, I mean, it's not each of the points. I guess it's for each of the points, right? So x minus x1, this x minus x2, this, sorry, the wrong one, this y, x, yeah, this, and x0 minus x1, so x0 minus x1, and x0 minus x2. So you do this for each. So for the second one is the same, but it's instead of from x0, it's going to be from x minus x0 instead, and x1 minus x0, x1 minus x2, and this is the same, right? So after you do this calculation, you essentially get a polynomial for each of it. Get one polynomial for, excuse me, L0, L1, and L2, which you then combine in the end by doing Px equals 4 times L0 x. Sorry, this is a bit hard for me to control. Let me just make this nicer. Yeah. So in the end, after you've gotten this 3 polynomial, what you do is you do Px equals 4 L0x plus, so y, so it's taking the first y value, essentially y0 L0x, y1 L1x, so y1 is 1 L1, sorry, x, and then plus the final one, 3 L2 x. Okay, so you can see it actually here. And then after you combine all of them, as seen here, I need to remove that notation. Then you can see that, hey, this is the polynomial that you get. So this polynomial represent a line, in a sense, a line that passes through these 3 points, right? Yeah, this is n plus this 3, so n plus 1, so this is 2. Yeah, you can also do the same thing for modular arithmetic, in which case basically this, but remember to follow the rules of mod, something that you're working in. in this case. Again, good example here. They are doing the same thing, but here is -4. So -4 under, I believe, is mod 5. Yeah, mod 5, it's 1, right? Yeah, so this divided by 1 will be just what's above, which is, wait, I think this is because of oh yeah, 2 times 3 is 1, yes, in this case. Yeah, it's a bit weird though. Anyways, yeah, so it does the same thing, but it just honors modular arithmetic, which means that these are also behind all this. It's not really written, but they are technically something like this, right? So yeah, and this is this is technically mod 5. Yeah, but you usually won't really see this written out. It's usually said that, hey, this is operating in a field of modular 5. Okay, so yeah, same thing goes here. I do this calculation, I get x over 3 times this, and this becomes this because of the, so 3 times 1, 1, 3 times 1, 1. So in this case, let me calculate for a little bit. You get this from 3 times 1, yeah. I believe the result, let me just try to calculate this as well. So we should get x, oh, sorry. Times 1 modular 5. So this is essentially, because it's the inverse. Yes. So it's x squared plus 3x, and then inverse of 3, which is 2. So it's 2x squared plus 3x, and that's why you get this. So 2x squared plus 6, which doesn't exist, so it's 1. So it's 1x. That's why you get this. Yeah. So again, I'll put it in a little bit more clarity here. So sorry. So this became this because if you translate this, it's essentially if you do the calculation, this is essentially x squared plus 3x divided by 3, which is equivalent to x squared plus 3x, sorry, times 3 inverse, right? I mean, this is equivalent to 1 over 3 yeah. So, which is the inverse of 3 in modular 5 arithmetic is 2. So it's 2x squared plus 3x, which again, if you expand it out, is 2x squared plus 6x, which is 6x is essentially 1 in this case, plus x. Yeah. So yeah, that's essentially, I mean, it's very similar to normal arithmetic. It's just that you have to honor the mod 5, and inverses are treated. You can change them to essentially this. Yeah. Yeah. So do it for everything, and then do the same thing of 4 times L0, 1 times L1, and then 3 times L2. You get this very nice, very pretty polynomial without any fractions. Yeah, that's essentially what Lagrange interpolation is. So right now we're actually working with points. You can also work, you can also use it on, well, not really use it on polynomial. You can use it on the evaluation of different polynomials at a certain point, and you can essentially get a new polynomial that represents the value of that polynomial that you are interpolating, or the point of the polynomial you are interpolating, when given that point as an input. I think I'm speaking very abstractly here. Never mind, we'll cover this later on anyways. But yeah, you can use Lagrange polynomial to essentially create a new polynomial out of evaluation of other polynomials at a certain point. So you can take you can basically draw a line. That's what we're going to use in the future. That's one very useful thing we're going to use in the future as well. So you will later, like I'm just speaking, like I'm just talking about things that will happen. Now we can use this in that way. So in future we might have like multiple lines, okay? So like 1 line, 2 line, 3 line, right? You can use what we do here. So this is like using multi-points to get the polynomial. It's cool, but what's interesting is we can also use this calculation or the Lagrange polynomial interpolation to actually say, hey, let's say I want to, so this polynomial, so polynomial A evaluates to a certain value at 1. Polynomial B, sorry, this is 1, sorry, 1. Polynomial B evaluates to a certain value at 2, I suppose. Yeah, 2. And polynomial C, which is this really weird one, evaluates to this value at 0.3. And we can only just take these few points and then create a new polynomial via Lagrange polynomial to basically say, hey, I'm drawing this new polynomial that when at this point evaluates to the same value as polynomial A, but at this point evaluates to the same value as polynomial B, and at this point evaluates to the same value as polynomial C. Yeah, so this is something you will see in Graph 16 actually. But yeah, and some other ZK protocols. But yeah, this is where Lagrange polynomial is used, just to share a little bit. Yep. Anyways, any questions? No questions? Nothing? Okay, great. If there's no questions, that's essentially it for this session. Before we end, so let's set what's for next week, essentially. So next 2 weeks actually, we'll be covering chapter 4, which is algebra. If we do it fast enough in one session, maybe we can just cover like the entire thing. But yeah, please go back, go through this chapter. Go through this chapter. Try to learn as much as possible. I really appreciate any form of participation during the session. Ask questions. Tell me, like, ask question, participate in discussion, right? Wade was really helpful just now. Thank you very much on that. So yeah, I always appreciate it. We're all learning together. If you want to do all the examples, go ahead. That'll be great. After you do the example, you can also share like what you've learned. That would be great, right? But yeah, so for chapter 4, you don't need to do all the example. Okay, if you're asking if you need to do all the example, you don't need to, but I think they will help you learn a lot. Yeah, so next week we'll focus on algebra. And so there's a lot of things that are pretty interesting here. There are some that are a little bit more straightforward as well, but yeah, just go through them on your own pace. We'll see what we can cover next week. We'll go a little bit faster maybe because I feel like if there's not much questions, we can always go fast. If there's questions, we can go a little bit slower across this chapter. Then we'll see. Okay, so homework slash work for all of you for next week. Go through chapter 4. And then we'll come back again next Tuesday to learn. Before all of you leave me, there is also going to be a introduction to zero knowledge, or more like it's more like a Lepak session, I would say. It's more like a hangout session that also would have a small sharing on ZK, a small introduction and sharing on ZK next Saturday. So I'll share the link here in the chat in a second. Give me a moment. Move on to get the link. Sorry. Okay. Okay, so let me just paste it here. So there will also going to be a introduction, like the introduction zero knowledge session where in the hacker house at SS15 next Saturday. It will be in the morning, just before lunch. Yeah, you're all invited. Let's just hang out a little bit, talk about programmable cryptography, ZK, and yeah, it'll be great to see you all there. No pressure though. So yeah. Anyways, thank you very much for coming today. See you guys next week. Bye bye.
Thank you.
Thank you.
Thank you. See you.
Hi.